This is the third lecture in the series on approximation algorithms. A short review of what we have seen so far. So one of the approximation algorithms we saw gave us a two-factor approximation for metric TSP. We also saw a two-approximation algorithm for metric clustering. Having seen these algorithms, a natural question might be that instead of just getting a two approximation, is it perhaps possible that we can get a 1.5 approximation, say either for metric TSP or for metric clustering? Here are some possible answers, and these happen to be true as a matter of fact. So for example, for metric clustering, you cannot get better approximation than a factor 2 unless p is equal to np. So this is a rather interesting kind of a result, that it is not only is it hard to find fast clustering algorithms which accurately cluster, but even getting approximate clustering algorithms seems to be difficult, because we believe that p is not equal to np. Most people believe that. However, here is some good news. If you look at the Euclidean TSP, so which is a special case of the metric TSP, it turns out that you can get any approximation factor 1 plus epsilon. However, there is a catch, and the catch is that your running time will also depend upon epsilon. So essentially, there is going to be a trade-off between the running time and the approximation factor. Obviously, the closer you want the approximation factor to 1, the higher is your running time going to be. So the smaller the epsilon, the larger the running time. So this dependence will be captured somehow. We can evaluate that dependence, and in fact we can work with a wide range of epsilons, and that's what this result says. Such results are called approximation schemes, and this is what we are going to study today. Here is a quick definition. An algorithm A for a problem P is said to be a polynomial time approximation scheme, abbreviated as PTAS, PTAS, if the following conditions hold. First of all, A must now take two arguments. Of course, it has to take the problem instance, and it will return the problem answer, but it will also take in addition a single number epsilon, which is greater than 0, which is going to tell the algorithm how close an answer we want, how good an answer we want. So A is going to return a solution with approximation ratio 1 plus epsilon. The smaller we name this number, the better is our solution going to be. But as mentioned earlier, the time taken by A is going to be polynomial, and now it's going to depend on epsilon. So this polynomial may change with epsilon. That's the new addition. So the time is going to be polynomial. Okay, we are going to be able to do this for any epsilon, but the time will be a function of epsilon as well. So it's a scheme in the sense that you can operate anywhere. It's not just one algorithm, but in fact you can think of it as a family of algorithms defined by different values of epsilon. There is also a notion of fully polynomial approximation scheme, which is often abbreviated as FPTAS. Okay. And in this case, we require that the time should also be polynomial in 1 over epsilon. So yes, the time will increase as you reduce epsilon, but it will only increase polynomially. Here, however, the time can increase, and in fact it can increase much faster than any polynomial. So this is going to be something harder to do, or this is going to be something which is going to be faster for the same epsilon. Here is what we are going to do today. We will describe an FPTAS, or a fully polynomial approximation scheme, for the knapsack problem which we studied earlier. The time taken by the scheme is going to be O of n cube upon epsilon. So notice that this is polynomial in the size of the instance n. As always, we will use n to denote the instance, the size of the instance. It's also polynomial in 1 over epsilon. So it is n cube, read it as n cube times 1 over epsilon. So its dependence on 1 over epsilon is linear. So it satisfies this condition as well. So the time taken is polynomial in n, as well as it is polynomial in 1 over epsilon. And therefore, what we will get is going to be an FP task. And so we will be designing an algorithm which will be an approximation scheme. So it will take an instance as one argument, and it will take the number epsilon. It will return a solution with approximation ratio 1 plus epsilon, and its time taken will be this. Let me quickly remind you what the knapsack problem is. You have of course studied it earlier. The input consists of an array V1 through n. V stands for value, and V of I is going to be the value of the ith item. The second part of the argument is going to be an array W1 through n. So these are all going to be integers. V and W are both going to be integers. And W of I again is going to be the weight of the nth item. There is going to be a third argument, which is C, again an integer. And C is going to denote the capacity of a knapsack. For the output, we have to select a subset of these items 1 through n, such that the total weight is at most C. So think of filling this knapsack, but when we fill the knapsack, we should not exceed its weight capacity. Otherwise, the knapsack will tear or something like that. And we are only allowed to pick a subset of these items. And furthermore, we want to pick the most valuable subset. So whatever subset we pick, we add up the values of the elements which we pick, and that is the value that we get. And we want that value to be as large as possible. So it should be maximum over all possible subsets. You have of course seen this problem earlier, okay, and we have devised an algorithm for this. The algorithm was pseudo polynomial time, as we discussed some time ago, and in fact knapsack is NP complete. What we are going to do today is we are going to discuss a new algorithm. It is again going to be based on dynamic programming. So we will have a new dynamic programming algorithm. It will also be pseudo polynomial time. Okay. So that won't really work as an approximation algorithm. For one thing, it's not an approximation algorithm, it's going to be an exact algorithm. But the reason it won't work is that it will take pseudo polynomial time, whereas we want it to take polynomial time. So after that, we will describe how we can modify the input instance to this algorithm such that we get good approximate answers, but we get them fast. So that's going to be the interesting idea. The sort of new idea of today's lecture is going to be this, that we'll take a pseudo polynomial time algorithm and we'll use that, but instead of feeding to it the exact instance that is given to us, we will feed it a different instance, perhaps sort of an approximated instance, so that we will get the answers fast, although we will get approximate answers. So let me quickly go over the dynamic programming formulation that we have studied earlier, very quickly, and then I will tell you how our new dynamic programming formulation is going to be different. Here is the old formulation. So what we asked over there was, what is the best value we can get for each knapsack capacity C, little c, where c is an integer anywhere between 1 and c, 1 and capital C. So capital C is the integer given to us as a part of the problem instance. So if you remember the dynamic programming algorithm which we studied long ago, it was doing exactly this. For each value of c, little c, between 1 and capital C, it calculated what is the best value we can get. So basically the question was, for a fixed capacity, and we take different capacities, but in each individual question the capacity is fixed, what is the best possible value, or what is the largest possible value we can get? The new problem, or the new way of looking at this problem, is to ask a different question. The question which we are going to ask is, what is the lightest knapsack, and by that I mean what is the smallest capacity knapsack which we can use for getting some value v, okay? And we will do this for all values of this little v in the range 1 through v all. What is v all? Well, v all is the sum of the values of all the items. We are looking at this v all because at most we will be interested in filling all items. Beyond that, there is nothing of interest because there are no more items to fill. If we figure out what is the capacity needed to fill all items, we should really be happy. So this is going to be the kind of question that we are going to study today. And as you can see, it's sort of the complementary question. Okay, so here we ask the largest value for fixed capacity. Here we are going to ask the least capacity for the fixed value, or the lightest knapsack for the fixed value. I want to point out that if we answer these new questions, we will still get a solution to the original problem which we started off with. So these new questions essentially compute S of v, where S of v is the lightest knapsack for value v. That's exactly what is being computed over here for different values of v. And notice that S of v is an increasing sequence or a non-decreasing sequence. Now, the question that we started off with was to get the best value for a capacity C. So on the face of it, it might seem that this is the natural question to ask, and indeed it is somewhat more natural. But the point is that even if we answer these questions, we will be able to find this. Why? Because we simply ask what is the largest value v such that the size required for it is less than or equal to C. So clearly, this is going to be the value which we are going to get had we started out with a knapsack of capacity C in this question. So the idea over here is that even if we solve all such questions, we will be able to solve this question which we originally started off with. You might think that here we are obliged to solve many questions, even though our single question over here is there is just single question over here. But if you remember, if you go back to the dynamic programming algorithm we looked at, even to answer this single question, we really answered all these questions. So it's not that we are going to answer more questions this time. Well, we may not necessarily answer more questions over here. We are just going to answer a different kind of questions. And from those answers, as mentioned over here, we will still be able to get the answer to the real question that we are asking. So from now on, for the rest of the lecture, I am going to think of these new questions. And once we have the answers to these new questions, we'll use this idea to return the best value of capacity C, for capacity C. So basically, my new instances for each of these questions are going to be characterized by these three arguments. So we are going to have an argument W, the weight, the value V, and the target value, the target total value that we need, and we are going to have such questions for all such different V's. And our objective is going to be minimize the knapsack size. Okay, so it's going to be this kind of questions where we want the lightest knapsack for this fixed value V. So how do we solve this problem? Basically, you will see that the algorithm is actually the logic behind designing the algorithm is actually very similar to what we did for the more natural looking algorithm. Basically, we need to decide whether to include item 1, whether to include item 2, whether to include item 3, and so on. So we have a series of decisions to make. So this is what we want. We want the optimal solution to the instance W 1 through n, V1 through n, and V. And let's look at it as this search space idea. So we consider the search space for this big instance, which is W of 1 through n, V of 1 through n, and little v. So this is our search space. So what is contained in it? It contains knapsack capacities, or it contains solutions to such problems. Okay? So it contains feasible solutions to such problems. Now the feasible solutions to such problems can be of two types. Okay, so for example, we can have solutions which have value v. Okay, so everything over here must have value v, but maybe the solution contains item 1 or not. So there could be one set of solutions which contain item 1 and another set of solutions which contain item 1 and another set of solutions which do not contain item 1. So this consists of sets with value v not containing item 1, and this must contain item 1. Sets containing item 1. So we really want the lightest capacity set, the lightest weight set from this. But we said that this search space has been decomposed into two parts. So we could ask, what is the lightest capacity, the lightest set in this, what is the lightest set in this, and we could take the lighter of the two. This is precisely what has been written down over here. So we wanted the optimal solution to the instance W 1 through n, V 1 through n, and little v. And we can get that by picking the lighter of the solutions, or the solution with the smaller weight of these two solutions. Okay. So the first one is we look at this set and we pick the lightest solution in that, and that is over here. We pick the lightest solution in that, and that is over here. So if you remember, this is pretty much the idea we used in our original dynamic programming algorithm as well. Okay, but what can we say about these two things? We can say something rather interesting. So this first term over here consists of all solutions to this instance which do not have item 1. But what does that mean? That just means that we might as well be asking for solutions to W2 through n and V2 through n and V, because we are not using item 1 anyway. So this term is in fact exactly the optimal solution to this instance. So notice that this is interesting, this is useful, because we are heading towards a recursive solution. So a solution to this is being expressed in terms of a solution to a smaller problem. That's always good news. What about this? We want the lightest solution of value v having item 1. So we are looking at this set. We know that at this set of sets, this part of the solution space, we know that every set over here contains item 1. So we take that away, and what is left? Okay, so what is left are sets which do not contain item 1, but we also know that their value had better be this, v minus the value of 1. Why? Because every set in this part of the space originally had value little v. If they contain an item 1, and if we remove that item 1, their new value must be exactly v minus v1. So what remains in this part of the search space are sets which do not contain 1, but whose value is v minus v1. Okay. So we take the best amongst those and add to that the item 1. Okay. But what is the best amongst those? So the best among those is again an optimal solution to some instance. In fact, it's an optimal solution to this instance. So it's an optimal solution to W of 2 through n, V of 2 through n, and V minus V1. This is the knapsack capacity that, this is the value that we are seeking. Why are we seeking this smaller value? Because we know that we are, at the end, we are going to add item 1 to it. So if we add item 1 into it, the total value will become V, and which is the value that we want. Okay. So therefore, we take an optimal solution to this problem instance, we take an optimal solution to this problem instance, add 1 to it, and add the item 1 to it, and take the lighter of these two things. So that's basically the algorithm. Okay. So now all that we need to do is express this as a recurrence. Okay. Well, there is a slight catch. Okay. So when we do this, this V minus V1 could become negative. What does it mean? I want an optimal solution in which the value is negative. That doesn't mean anything, right? So we had better be careful about that. So we must generate this part, okay, only if V minus V1 is greater than or equal to 0, because otherwise this problem instance is undefined. So when we write down our recurrence, we will have to put an explicit check whether V minus V1 is greater than or equal to 0 or whatever, greater than or less than 0. Okay. Okay, so here is the expression in terms of which we are going to define our recurrence. So SIV I am going to define as the least capacity knapsack which can give me value V using items I through n. So this I defines this I, this is the same I, and this V defines the value that we want. So SIV is going to denote the least capacity knapsack which gives me value V using items I through n. So now I'm just going to take this expression that we derived and express it in terms of this kind. So what is this optimal solution to WVV? Okay. Well, this is simply, this left hand side is simply S1V, because we are starting with I equal to 1, we are allowing all items and we are asking for value V. Then we are going to take the lighter of the solutions. So correspondingly we are going to use the minimum over here, okay, the minimum of two solutions. What is the first solution? The first solution is to the instance W2n, V2n, little v. So it's going to be the least capacity solution to this instance. So that's as good as saying it is S2V. So that's what we have written down over here. The second part is this. However, when we write this down, we have to make sure that V minus V1 is not less than 0. So let us check that. So I'm going to write down a C style expression. Okay. So this says that let us check whether V minus V1 is greater than or equal to 0. If it is, then the value that we want here is W of 1 plus S of 2V minus V1. Why is that? Because we are going to have item 1 always, and therefore we are going to have the weight corresponding to item 1 always present over here, and we are going to add this item 1 into the optimal solution to this problem. But the weight of that optimal solution, okay, the capacity needed for that optimal solution is simply S of 2. We start with items 2 through n, and therefore this is a 2 over here, and the value that we are expecting is V minus V1, exactly this. So if this expression is greater than or equal to 0, then this is the value that we want. If this expression is less than 0, this problem is undefined. But how do we represent that? Okay, so that we represent by putting in an infinity. So we are taking the min, this infinity will never be taken, and if this second expression is infinite, then that's as good as saying just give me the first expression. Okay, so this is what we have distilled out of this. Well, it's actually the same thing, but it's now written out more compactly in terms of variables of this kind, okay, subscripted expressions of this kind. We must of course generalize it. In order to use it to design an algorithm, we need to generalize it. Okay, so here is the generalization. So here we were looking at all the items 1 through n. And you can see that internally we needed to have solutions to problems in which we were having items 2 through n. If we did recursion on that, then we would get 3 to n, 4 to n, and so on. So therefore, we now consider the more general case. So we are going to ask, what is the least capacity solution of value v using items I through n? So that is S of iv, that is denoted by S of iv. So analogously, we will write down the expression, the more general expression. So here we skip the first item, and so we started off with 2. So similarly here we are going to start off with I plus 1. Okay, so that is the first solution corresponding to this. Okay, and instead of checking whether v minus v1 is greater than or equal to 0, we are simply going to be checking whether v minus v of I is greater than or equal to 0. If so, here we took w1 plus something, here we will take wi plus something. Again, this something is going to contain items 2 through n over here. It will contain items I plus 1 through n over here, and so we will have I plus 1 over here. This was the value required was v minus v1. Here, the value required is v minus vi, because we are adding in item I later on anyway. Okay, so we want v minus vi, that is the value of this part, and then to it we add item 1. So the weight solution value of this whole thing together will be w of I plus S of I plus 1 v of v minus I as before. And of course, if v minus vi is less than 0, then we don't want this entire term to be taken into account at all, and therefore otherwise we are going to put down an infinity. Okay, so this is the defining recurrence that we are going to use. So let us see how this recurrence can be solved. Okay, so as usual we are going to be keeping a table. Okay, so I have just written out that recurrence again. So let us see what kind of table we can use for this. So here is the table. This is the I axis going down vertically. This is the V axis. Okay, so earlier I said that V really needs to start from 1, but it's useful to have a 0 here as well. Okay, so I have started it off from 0, and as before it goes to V all. So since we are going to have, since I want to show you what this recurrence means in this table, I have put down some specific, and I have marked out some specific entries. So let's ask how this recurrence will work out in this table. So I want to compute S of iv, which is this entry in this table, ith column, vth row, ith row, vth column. Now this entry depends upon which entries? Well, it depends upon this entry, and it depends upon this entry. We just don't have to look at this entry, we have to do something to it. But this other thing that we have to do, we know what the value of wi is. So it really depends upon this entry and this entry. Okay, so which are these two entries? So this entry is this entry, and this entry is this entry. Okay. Of course, if v minus vi was less than 0, then this entry would fall outside the table, and so we would only have a single entry over here. But this is the more common, more interesting case. So to fill this entry, it is sufficient if we have this entry and this entry filled. That's all coming out of this recurrence which we have written down over here. Well, that suggests a way of filling in this table. So we sort of fill in going bottom up or bottom right from, we start off at the bottom and go upwards, but we also need this, and so therefore we also have to start from the left side. So to do that, we would need to have these entries filled. How do we fill these entries? Well, let's interpret what these entries are. So this entry in general is going to be Si0 for different values of I. And let me remind you what Si0 is. Si0 is the capacity, the minimum capacity needed to get a value of 0 using items I through n. That doesn't seem too difficult, does it? We just want to get a value of 0. So what is the minimum capacity we need? Well, trivially, the answer is 0 capacity. Okay, so if we get capacity, if we get a knapsack of capacity 0, okay, we can certainly get value of 0 by filling nothing into it. And clearly, there is no smaller knapsack that we can use because this is the smallest possible knapsack. So this entire yellow column just needs to be filled with zeros, and that's something we can do without any computation. So that leaves open the question of how do we fill this row. So let's try to interpret what this row is. So this row in general is going to be S and V, which is denoting the capacity needed to get value V, the least capacity needed to get value V, using item n alone. So you are just allowed to pick item n, nothing else. So what kind of capacities can you get? What kind of values can you get? Well, clearly, if this V happens to be V of n, then you can do that using just a single item. Okay. So that would mean that if V happens to be V of n, then the least capacity knapsack that you would need would have to have capacity W of n. So one of these entries can be filled using this. What about the rest of the entries? Suppose we want to do this for a different value of V. So let's say we want to get a value larger than V of n. Can we do it? We are only allowed to use item n. So clearly we cannot do it. We cannot get a value either bigger or larger than V of n by using only item n. So then what do we do? So that can be represented quite nicely by saying that, by putting in an infinity in these entries. So V of Vn, so if V is not equal to Vn, then we cannot get that value. And so we will say that a knapsack of capacity infinite is needed. Okay. Let me explain why this works. Basically, later on we are going to take things like min of this and min of this or something like that. So if there are infinities over here, then that value is essentially going to be ignored. Or if both of these values are infinities and if you take min of those infinities, then an infinity will crop up over here, but that says that even this value is impossible to accomplish. So that's sort of a nice thing, that's kind of a nice coding that infinity allows us to accomplish. So basically now we have expressed the algorithm entirely. Okay, so we have entries to fill, and there are sort of three kinds of entries to fill. We have these yellow entries to fill, we have these blue entries to fill, and then there are the rest of the entries which we fill according to this recurrence. So we can write down our algorithm. So I'm going to call my algorithm KS, knapsack. It's going to take as argument. Okay, so that brings us to our algorithm. We'll call this KS for knapsack. It takes as arguments the value, the weight of all the n items and the capacity. So we are going to find an answer to this, but we are going to find an answer using our new formulation. Okay. So as mentioned earlier, okay, so there were those yellow entries to be filled. They were all going to be filled with zeros. So we'll do that. Okay, so these entries using this equation. Okay. Then there were the blue entries to be filled. Okay, the blue entries were that for if V is equal to V of n, then the knapsack capacity needed was W of n. Otherwise, the knapsack capacity needed was infinity. So this is how we fill the bottom row. So this is how we filled, and this was the equation used. Okay. Finally, the rest of the entries were filled using the recurrence which we derived. So this is that recurrence. At the end of it, to get the value for the capacity C, we needed to find, as we described earlier, the largest V such that SV1 is less than C. So what is SV1? So we look at all possible V's. So this is column 1, and we know that as we go down, this is going to be non-decreasing. So we can easily find the largest V such that SV1 is less than C. Okay, and that is the value which we will call V star. So that is the value that we are going to get if we in fact had a capacity of C. So if we were just interested in the value, then we would be done at this point. However, if we wanted the items to be returned as well, then we can do that also. You remember how we did that for the older algorithm. We just had to keep track of some additional pointers, some additional data structures. Basically, we can do that as well. So corresponding to every entry of the table, we can determine what the corresponding set is going to be. So we can also return the set of items. So how long does it take just to compute everything from here until V star? Well, this loop will take time O of n, this will take time O of V all, and here we have nested loops, okay, and therefore it will take time O of n times V all. In fact, if you compute the set itself, we'll have to keep some additional data structures, but as explained in the previous algorithm, we can use exactly the same ideas to compute the set as well in exactly the same amount of time, well, to within constant factors. So in O of n times V all time, we can not only compute V star, but we can also compute the corresponding set. So this entire problem can be solved in time O of n times V all. Okay, so that finishes the first task that we undertook. So we now have a dynamic programming algorithm which finishes in time n times V all. So now we come to the approximate algorithm. Here is the important point. So here we are going to be allowed an error in the answer. We are only required to get within 1 plus epsilon. So epsilon is sort of the error we are allowed. The point is that if we are allowed an error, then it means that we can calculate using low precision. So basically, we are going to calculate using low precision, and that is going to allow us to reduce the time. So we are going to write a new procedure, a new algorithm, which we are going to call approximate KS, approximate knapsack, or AKS. It's going to take the same arguments as before, but it's also going to take an argument called delta, which is somehow going to reflect the precision. And we will tie it up to this epsilon later on. So delta and epsilon will be related. How they will be related, we'll specify pretty soon. Here is the algorithm. So we are going to define a new array, V prime. So V prime is simply going to be V divided by delta, corresponding elements. Okay, so every element here is going to be divided by delta, and we get the corresponding element of here. But we want V to be integer as well. So if we get a fraction, which we will in general do, we'll take the floor, we'll take the largest integer less than, okay, or the floor. And then, so essentially we are scaling down the V values by a factor delta. We will call Ks using those scaled down values. But the scaled down values are not really going to be important for the final answer. So for the final answer, we want to return delta times whatever scale down values we got. So this is expected to do roughly the same job, right? We scaled the values down, we got a good solution, and then we scaled the values up. The only catch is that here we took the floor. So this will produce some error. Okay. At the same time, since the answer, the time taken for this case is proportional to the second argument, the time over here is going to be v prime rather than v. So that's where we are going to save on time as well. So we'll save on time at a cost of some error. So what remains now is to analyze all this. Let's say that S denotes the set returned by our original KS call. So where we were using the actual values of V as given. So this is truly the optimal set which was returned, and its value X is the actual optimal value. And I can think of this as the full precision problem, or the full precision answer as well. S prime is the set returned for this problem, okay, by this KS, without multiplication by delta for the minute. Okay. Let's say its value is X prime, and this is the low precision answer. So what we now need to do is to relate this X prime that we get, so X prime and X and so on. So let's just do that. So I observe first that X prime is the value of the sets over here, value of the set over here. And what is that? Okay, so it's the values of all the elements in the set. So V prime of I, because this time we had passed V prime, where I belongs to this S prime. Now here is the important point. This X prime, this value, is bigger than this expression as well. Okay. Notice that the only difference between these two things is that instead of choosing S prime, I am choosing S. So this was the optimal set which was returned. This is not the optimal set, but it's some different set. Okay. So what happens if it's a different set? So its value need not be as big as the value of this. So in other words, this value has to be at least as big as this value. But notice that this S was an acceptable solution to this, and in going from here to here we have not changed the weights. So, so this set is also an acceptable solution to this. So therefore, we can clearly say that this value had better be no smaller than this value, because this is also a feasible solution to the V prime problem as well. So S is also a feasible solution, and therefore we get this. Now finally we observe that if I take the floor of any number, it is bigger than that number minus 1. And therefore this is the floor of this, and therefore this is bigger than this minus 1. Okay? So V prime of I is the floor of this, and therefore V prime of I is bigger than V of I upon delta minus 1 because of this. So we have been able to relate X prime to this quantity over here. Okay. So the point is that we are getting towards the optimal set. Somehow we want to relate it to the value of the optimal solution. So let's now ask, what is the value that AKS will return? AKS returns delta times this value. Correct? Delta times this value. This is what we do over here. Okay, and what is that? So delta times that value, well, for X prime I am going to substitute this, so I am going to get this multiplied by delta. So if I multiply by delta, this delta is going to get cancelled out, so I get a VA minus I, and instead of this 1 I am going to get a delta because I multiplied by delta. So that explains this part. Now what is summation over S of Vi? That's simply X. Okay, so I get an X over here, and there was a minus delta, but it was also in the sum. So my delta is a constant. Delta doesn't vary depending upon which element of the set I am considering. Okay, so I will get minus delta as many times as the cardinality of S. So I am going to get x minus cardinality of S times delta. So here is an important observation. We have proved that the value returned approximately is at least the actual value minus cardinality of S times delta. So now we are ready to evaluate the approximation ratio. What is the approximation ratio? So it's on the value of the returned value, upon the value of the value returned by the approximate solution. Remember that this problem is a maximization problem. Therefore, the optimal solution has the largest possible value. And in that case, we define our approximation ratio as the optimal solution upon the approximate solution. So that's exactly what we are doing over here. So we want the approximation ratio of x upon y. Okay. So let us collect the inequalities which we had over there. So we had one inequality which is y is greater than or equal to x minus cardinality S times delta. Okay. So this is one inequality, and I can write this as x is less than or equal to y plus cardinality of S times delta. If I divide the whole thing by y, I am going to get x upon y is less than or equal to 1 plus cardinality of S times delta upon y. This is what we are going to get. So this is what we finally have over here. What is the time taken by AKS? Okay, so it's n times v prime all, okay, or v prime all is essentially v all by delta, so it is this time. Okay, so notice that the time over the exact evaluation has reduced by a factor delta. So all that remains now is to choose delta carefully. Now here is the clever choice. We are going to choose delta equal to epsilon times v all upon n squared. Okay, so let us just do that. So we choose delta equal to epsilon times v all upon n squared. So what does that do for us? So first of all, this was our approximation ratio. So if we substitute into that, what do we get? So we substitute delta upon y over here. So we get epsilon v all, and then this the y remains as it is from here, and we get an n squared over here. So this is the approximation ratio. So what becomes to this? What becomes of this? I claim that this becomes at most 1 plus epsilon. Why? So let's see that. The first observation is that the cardinality of S which appears over here has to be less than n. After all, what is S? It's a subset of n elements. So its cardinality has, of course, to be less than n. Okay, so that's one important observation. Then second, V all is the sum of all the elements. So clearly it has to be less than V max times n. So if V max denotes the maximum value, if I multiply it by n, I certainly should get something which is bigger than just the mere sum of values. So this is what I get. And I claim that V max cannot be bigger than y. Okay, so the maximum item had better be accommodatable in my knapsack. Okay, otherwise, I would not have considered it in my list in the first place, and therefore, the optimal solution had better include this largest item, and therefore V max times n has to be at most y times n. So it follows from this that S times V all is less than y times n squared. So this S times this V all is less than y times n squared, and therefore our approximation ratio is 1 plus epsilon. I also claim that the time taken is n cube upon epsilon, and this is much easier to see. So time taken is n times V all upon delta. So I just substitute and I get Instead of delta, I substitute this, so this V all cancels, and then I get an n squared here, so I get n cube upon epsilon. So what has happened? We have shown that our approximation ratio is 1 plus epsilon. So no matter what epsilon you give me, I will be able to get this time if I choose delta equal to this in my procedure. And furthermore, my time taken is going to be n cube upon epsilon, so which is exactly what we had promised. We had promised to get an approximation scheme in which the approximation ratio is 1 plus epsilon for every epsilon, and that we would prove that the time taken is polynomial in n, the input instance length, and 1 over epsilon. That is what we have done. So that concludes the main part of the lecture. I just want to make a few remarks. Our FPTAs had time of n cube upon epsilon. It is possible to devise another FPTAs with a different expression, n log 1 over epsilon plus 1 over epsilon to the fourth. So it's very likely that in practice this approximation, in many practical situations, this might be a better algorithm than this. But this is of course more complicated as well, and we are not going to look at it. Now here is an interesting fact that suggests that somehow that knapsack problem is actually among the easier NP-complete problems in the following sense. Knapsack problems in which weights and values are drawn uniformly at random from the interval 0 through 1 can be shown to take polynomial time on the average. So in some sense, the FPTAS result says that it's easier to approximate, and this says that it's also easier on the average. In fact, it's polynomial in the average. Finally, I just want to say that many problems having pseudo-polynomial time algorithms, even if they are NP-complete, can be shown to have a PTAS or even an FPTAS. Another example is the subset sum problem. Thank you.